Yeah, very good morning. We can start now. Okay. Yeah. So I have left on you that to see whether this table matches with your solutions or not, and I hope you have done that exercise. Okay. Now let's. We have defined jointly two random variables. How will you write their joint PMF, right? Where both of them are discrete. Okay, and we have dealt with two examples. Okay, and I hope we have gone to detailed discussion about them. Okay, right. So now in the similar fashion, we can also talk about the jointly continuous random variable. Okay, so we say that let me so we say that x and y are jointly continuous. Okay, we say that x and y are jointly continuous if you are able to identify a non-negative function. So you are going to have double integral, you can see, okay, on R2. So they are real valued. So now if you extend one more variable, so it's going to be in R2. If you extend on one more variable, means three random variables, you have three variables and it is going to be in R3 and so on. Such that, so this C can be any region occupying in the plane. Okay, that R square. So we are going to perform the double integral over this xy, where this limit of integration you can identify when you have a specific region of integration. Okay, so I hope that you have done many times in your vector calculus and integral calculus somewhere. So I don't think so there is any problem to understand that how do you find this limit of integration and all. Okay, and then you can apply that change of variable and so on if you have any struggle in evaluating this type of integrals. Okay, so whatever we have talked about, all these things can be extended to any finitely many random variables. Okay, so x and y, so you have two. So if you have n, so you have n time integration here. Okay, and so on. Okay, similar for the double sum, and you have you have seen that how would you have identified this for the case when you talk about the jointly discrete random variable. So there you have seen double sum. Here it is double integral. Okay, and when you cover the vector calculus or integral calculus, you have also seen that how double sum converts to the double integral, or triple sum will convert to the triple integral, because your computer will not understand what is this analytical integral meaning. Okay, you have to approximate. So double sum is there anyways. So that detail I don't want to go here. Okay, so let's understand this as a definition. So this fxy is called joint PDF of x and y. And you can have this, certainly when you talk about the PDF or PMF, okay, of certain random variable x and y, you certainly look at their distribution function, cumulative distribution function. Okay, so this is already has been defined. The definition is x less than equals to a and y less than equals to b for this particular case. Okay, and if you identify this x less than equals to a, what is this? This is this integral on the real line by this closed interval, that's minus infinity to close it. Similarly, this y less than equals to b stands for this. Y lies in this range. Okay, and means together x comma y lies in the following. That you know what is this cross meaning here. Okay, this cross is the Cartesian product. Okay, so that is written here. Means first element is from the first set and second element from the second set. Okay, so this is your C now, and you can now certainly put the limits here. So minus infinity to a for x limit and minus infinity to b here second limit. So it may be variable limit also sometimes, means when you do tackle with some certain type of problem that we will also look at later. But so far you have the only constant limit of integration. Okay, right. So I don't think so we have to say much about it. Okay. Now again, this is is the continuous manner of, is like what we have discussed in the case of discrete random variable. So if you are going to if you're going to take the y where limit is infinity, okay, means like this is this symbol, I think x a comma infinity. It is it can be understand that x is less than equals to a and y is less than, which means y you are taking the whole range. Okay, so if you do that, you are going to give the marginal CDF, okay, of x if you are varying y over the whole sample space. Okay, so if you are going to vary the a, okay, the x variable over the whole sample space and keep y is which, you will get the marginal CDF of y. Okay, right. Now you also know the relation between the CDF and PDF. Okay, so for the single variable case. Okay, so that is nothing but the derivative of, right, fx dash of a will give you the small fx dash of a, small fx of a. Okay, right. So this is this is some here it is giving you the definition of marginal PDF of x. How will you get it? You are going to integrate with respect to y. So this is in the C. This is in the means you have seen this type of things already in your discrete case. When means you are summing, you are covering y over the whole sample space. So this is what it is meaning. So you are covering y over the whole sample space. If you carefully look at the limits of y, it is minus infinity to plus infinity. If I integrate with respect to y or to the joint PDF, you will get the marginal PDF of x. If I integrate with respect to x over the whole sample space, okay, then it is going to be marginal PDF of y, and so on. Okay, so these things already have discussed in detail for the discrete case. Okay, right. So this is a, you can say, continuous version that you have. So you can say the limiting case it is going to happen. Right. Okay, so these things I just now mentioned, that if you take variably that x you are ranging over the whole sample space, means you are going to get the marginal CDF of y. If you are integrating the joint PDF over with respect to x over the whole sample space, then it will give you the marginal PDF of y. Okay, right. Right. So now means this is all we have talked about, right? Means once you know the marginal PDF of x, you can certainly find out the respective probability of x inside the region B. Okay. So I don't think so here any. If you have any doubt, you can ask. Okay, here it's very straightforward. It's only following these two lines. Okay, once you know the marginal PDF of x with respect for a x random variable, you can certainly evaluate this by following the definition. Okay, or if you, so see, this is required to find out, or else you can also, means you take y limit over the whole sample space and x limit over the set P. If you don't want to go with this, you will automatically get down to this, okay, in the evaluation part when you are evaluating this. Okay, so either you find out the marginal PDF of x first and then you are integrating over the region P. Okay, or you can follow this. You can write this, right, and you can get this. Okay, this is only just the definitions. Okay, right. So it is now this is already I have done, so I don't want to. Yeah, okay. Let's come to the problem. Okay, let's see how we will handle the problem. Okay, right. Okay, this is an example. Just a second. Yeah, it's moving now. Yeah. So you have this exercise example. So the joint PDF of X and Y random variable is given to you. Okay. You can verify that this is non-negative function, and also double integral, okay, over the whole sample space for X and Y. Double integral, if you go with it, uh, that you can verify. Okay. So you can this is I can say here that you can verify that double integral minus infinity to plus infinity minus infinity. That normality condition you can say fx comma y of x comma y dx dy is equals to 1. That you can verify. Okay, you know how to perform the double integral. Okay, now your first problem is you have to identify the first problem, that find probability of x greater than 1 and y less than 1. Okay, so certainly you have to write down in the proper way, and then you can use this joint PDF. Okay, right? So here it is. Okay, so now if you carefully see this x greater than 1 and y less than 1. Okay, what it is, x is greater than 1 means x lies in the interval 1 to infinity. X greater than 1 means lies on the right of 1, right? And y is less than 1 means y is lies between minus infinity to 1. Okay, so this x is lies here and y is lies here, so together it will rise to the following region. X is from 1 to infinity, this Cartesian product 1 comma infinity cross minus infinity comma 1. In some sense you can also say this is a some kind of rectangular region, upper rectangular, or okay, infinite length. Okay, right? So this is the reason B, so over which you are going to integrate. So this is now you are following the definition here, that double integral over this B, and that you are double integral for the joint PDF. So you have this joint PDF to you. Okay, so B, so you can, so these are both are constant limit, right? So this is your choice whether you first want to integrate with respect to x and then with respect to y, or with respect to y first and then with respect to x. Okay, so here it is first with respect to x and then with respect to y. Okay, x limit is from 1 to infinity and y is limit from minus infinity to 1. Now go back and check this the definition. So it is 0 whenever x lies on the right of 0. Either one of them is right of 0. Okay, then it is going to be 0. Okay, so minus infinity to 0, this limit, if you break down minus infinity to 0 and 0 to 1. So minus infinity to 0, this is 0. So no need to evaluate this integral. So you have only 0 to 1 left. 0 to 1, 1 to infinity, fx of y, dx of x comma y, dx. Now, for x, 1 to infinity and 0 to 1, you have to evaluate this over this region. Okay, right? So now you substitute this fxy here, that is 2 times e to the power minus x times e to the power minus 2y. Okay, right? So now substitute here in the integral and solve it out. Okay, so if you substitute e to the power minus x times e to the power minus 2y dx dy, okay, now you can integrate. Now these are constant limit, and you can write in this following product form as well, so that you know, I think by your experience. Okay, or you can first, you have to integrate first with respect to x. So e to the power minus 2y is out. Integrate e power minus x over 1 to infinity integral. So this is an improper integral. Okay, one of the limit is infinity. Okay, so how will you evaluate this? Okay, so this is here is the procedure I have written down. So again, so if you recall, improper integral of this is first kind. Okay, so one of the limit is infinity, so you have to put that a, evaluate that, and letting limit a tends to infinity. So you can integrate this properly. Okay, you can integrate this, put upper limit minus lower limit. Okay, and then letting a tends to infinity, that is going to be give you the value 1. And then so this value is going to be constant 1. Okay, now only remaining this e power minus 2y dy, and you know this is not an improper integral, this is definite integral because none of the limit is infinity, and inside the interval it is a well defined function. Okay, so you can integrate easily e power minus 2y, right? E power minus 2y divided by minus 2 and put upper limit minus lower limit. So you are going to get the following. So the answer means this is the final answer for this one. Okay, right. So this is how you will handle the first problem. Okay, now the second problem is little interesting, that you are interested in finding the probability of x less than y. So this is again the how will you read this x less than y? Okay, this is an abuse notation. So what is x less than y? X less than y is going to be the set of all w in omega such that x of w is less than y of w. Okay, right? So these are the real values. Okay, this is the abuse notation of this. Okay, we will come to this third problem later. Okay, so this is x less than y is going to be this set. How will you handle this now? Right. So first of all, what I think, yeah, this is not a ratio. So this is fine. X of w is less than y of w. So if you look at the, so these are the values, right? So x of w equals 2. So you see how will you draw this? Okay, how will you find out the limits? You need to identify the limits of x and y. Okay, right? So so here you are going to get a variable limit. Okay, so let's see. Okay, you have this here, x less than y, and you know you can on the R2 plane you can certainly draw x equals to y. Okay, and what is x less than y here is this, right? This side. Now you know x is 0 to infinity and y is 0 to infinity, then only it is non-zero. Okay, so you have this reason. So I can certainly identify the reason is this, x comma y such that x is less than y. Okay, so now you can find out that, so this is the only, so this is the only reason. Okay, this is the reason only. Okay, where this fx of y is non-zero, you can say. Other means below one also is the reason, but this is the reason where fxy is non-zero. So now over which, how will you integrate? Okay, so how will you find out the limit here is, you have this is x equals to 0 to x equals to y, right? X equals to 0 to x equals to y, and x limit is from 0 to infinity. If you have any problem here, you let me know.
Sir, wouldn't the region be the upper region?
Yes, sir. Won't it be the upper one?
Upper one. Wait a minute. X equals to, yeah, it's upper region. Yes, right. Right. Yes, x equals to x is less than y. So it is going to be, because here is x is getting positive. So you have this is x is right. This is the problem. X less than y, this side. Okay, x greater than y is this side. Okay, now this is the reason where you have to work. Right, you have to work on this. Yeah. Yeah. This is one. Okay, over which this joint PMF, so joint PDF is non-zero. Otherwise, it is zero. Okay, now if you look at the limits, okay, if you look at the limits, so x equals to 0. So on this line, right, you have this is right, this is the reason. Okay, it's an infinite length, you can say rectangle, you can say, sorry, triangle. Okay, right? So what it is here, you can find out the limit is if you draw here. Okay, so x equals to 0, this is x equals to 0 to x equals to y. X equals to 0 to x equals to y, and y limit is from 0 to infinity. Okay, right? So this is going to be non-zero over here. So this is now further this thing you can verify now this integral. This is a improper integral because of the one of the limit is infinity. Again, you have to handle in the similar fashion and so on. Okay, I will give you the final answer. You can verify by evaluating the integral. So do you have any issue here in the limit now? If you have any issue, you can talk. Okay, fine. Right. So this is the final answer. Okay. Probability of x less than y is 1/3. That's going to be final answer. Now, the third problem was to identify what is the probability of x less than a. So there are two ways. Either you find the marginal PDF for x and then evaluate it, or you can straightforward, you can write it x less than a and y over the whole sample space minus infinity to plus infinity. Okay, now integrate fx comma y. Okay, it means with respect to x and y both. Now both are constant limit. You can first integrate with respect to x and then with respect to y, or first with respect to x, with respect to y and then with respect to x. The choice is yours. Now from here it is clear that x is belongs to minus infinity to a. Okay, and y is belongs to minus infinity to infinity. So this is what the integral limits now. And now you apply the definition of fxy. You know it is non-zero only on the positive side. Only in the, you can say, is the first coordinate of the plane. So you have 0 to a and you have here is 0 to infinity, the next level. Certainly, if a is less than 0, it is 0. So you can discuss then afterwards that cases that a is less than 0 or a is greater than 0. Okay, and so on. Okay, so certainly here the results to be distinguished. Okay, whenever a is less than 0, it is a, you have as a x less than 0. Okay, then you have this is less than 0, y is belongs to minus infinity to plus infinity. So you have minus infinity to 0 over this range, fx of y is 0. So straightforward, for a less than 0, it is 0. So is equals to 0 if a is less than 0 or equals to y. Yeah, equals to also is the same, because in the continuous case, the point does not matter. Now, for the case a strictly greater than 0, then you have to evaluate this integral, right? So this is the final one is you have the limit is you have this is 0 to infinity, 0 to a, fx comma y of x comma y dx dy. Now, if a is less than or equals to 0, this is 0, and if a is greater than 0, you have to integrate. Okay, right. So we have this is here is this is what is I think this what is I have evaluated is the CDF of x. Okay, so whenever you are talking about a continuous random variable, most of the time people start with finding the distribution function. Okay, cumulative distribution function. Okay, this is again in the same way. Okay, in the same fashion, so you can identify this is going in the same fashion. Okay, so what I have we have this is less than a and that is less than equals to a. Okay, so instead means this is nothing but the cumulative distribution function, right? Right. So this is what is the notation here. Okay, so you are going into the same flow. Okay, so here it is going to be when you have a is greater than 0. Okay, and 0 whenever a is less than 0. Okay, so a is greater than 0 and 0 if a is less than equals to 0, right? And you can see when a is going to 0 plus, again it's going to be 0. This is continuous at a equals to 0 as well, this function. Okay, we can discuss about the nature of this function. Okay, right. Okay, so now we have done with the jointly continuous random variable. Now let's talk about the independence of two random variables, and that again similarly you can extend the definition for finite case, any number n number of random variables. Okay, so when you have talked about in the case of probabilities, when you say the two events are independent, means probability of a into b is equals to probability of a into probability of b. Okay, so this is going to be, so this is nothing but this is the same situation here. Okay, so this is a x less than equals to a and y less than. This is how the joint distribution or joint random variables are defined jointly. These two random variables are defined jointly with respect to the following type of distribution function. So you can talk about here continuity in the similar manner. Okay, right. Independence of the random variable in the similar manner. Okay, so you have the following definition. Okay, and it is easy to follow. So we say that random variable x and y. So you have taken two random variables x and y, and are independent if you have the following result. And I think this is easy to follow if you have followed the definition of the independence of two events in the case of probabilities. So this is x belongs to a. This is a comma here, means you have x belongs to a and y belongs to b is equals to probability of x belongs to a into probability of y belongs to b for any AB subset of R. Okay, for any. So this also matter. You take any A and B from the subset of R, and if this is happens, then you say that x and y are independent. Okay, right. So this is in terms of, you can say this is nothing but the in terms of PMF or PDF also you can extend this definition. CDF also you can extend this definition as follows. I'm just going one by one here. So in terms of joint CDF, x and y are independent if this C. You can easy to follow the following. Okay, the definition of this fx, this joint CDF is x less than equals to x and y less than equals to y. Okay, so x is lies in the range minus infinity to x and y is lies in the range minus infinity to y. And if you rewrite all the things, okay, everything is x comma y belongs to minus infinity comma x cross with minus infinity comma y. This is the specific reason of R2. Okay, Now, if you follow the previous definition, this is nothing but the probability of if it is follows. Okay, if it is true. Okay, if it is true, if this happens is equals to means probability of x less than equals to x into probability of y less than equals to y. Or in other words, if it is equals to marginal distribution for product of their marginal distribution functions, then you will say that x and y are independent random variables. So again, if you have n random variables, you have x1 comma y x2 comma x0 xn. If you are able to write their joint distribution as the product of marginal distribution function, fx1 of x1 into x of fx2 of x2 and so on fxn of xn, then we'll say all of the random variables are independent. Then you can talk about pairwise independence. You take any two random variables and their joint distribution is can be written as their product of the marginal. Okay. Then that means that you can define the pairwise independence. Okay. Now this is in terms of joint CDF. In terms of joint PMF, so again you can talk about the joint PMF. So if you follow the definition of joint PMF, means you are talking about the discrete case. Okay. So xi comma yj, so this I and j are from the index set. Okay, one of the values. So x and y will take the values from the set. You have x1, x2, and so on. And y takes the values from y1, y2, and so on. So this can be finite set or countably infinite, we don't know. But you take any two here xi comma yj, you can write in terms of probability. If you can write the joint PMF as the product of marginal PMF, okay, for all values of x and y, then you can say those two random variables are independent. Okay. So in the similar fashion, you can write for the continuous case. Okay. So I have given you the definition of independent in terms of CDF, PDF, PMF, okay, and original definition. Okay, right? Right. So let's have the following example. Let's see how we will use this independence, okay, of two random variable in the problem. Okay, right. So you have the following exercise. Okay, so let x and y are two independent random variables and that have common density function. So they are independent random variable and both share the same density function. Okay, both share the same density function. Yeah. Then you are interested in finding the PDF of x by y, x divided by y. Now you will say, how will we define this x by y? This is a quotient of two functions, you know, right? And you know how when it is valid, when you have denominator does not vanish in the domain, right? So you have to make sure that y should not vanish inside the domain. So it is not, right? Okay, x and y will never be zero. Okay, you are not going to take the case when y is zero. Okay, so you are interested in finding the PDF of x by y. Okay, right. So since it's a continuous case, certainly we will look at first the CDF of this x by y. Okay, and then we will take their derivative and we will have the PDF for this random variable x y. So since x and y are random variables, so this together will also identify a random variable. So there is no question about it. Okay, right. So let's talk about the joint CDF. So in the case of A less than equals to 0, you have to discuss the case. Okay, for x greater than 0, it is x or y greater than 0 e to the power minus x. Otherwise, it is 0. So we are only talk about the range when you have x by y is greater than 0. Okay, it is A less than 0. It is not possible. Okay, we are now just removing that. Okay, so it is 0 if A is less than equal to. That's, I think that's just straightforward because it's an impossible event. Okay, because if you follow the definition of x by y is A is less than equals to A is less than 0, x by y is less than equals to 0, it is not possible. It's an impossible event. Okay, now if you read this this abuse notation carefully, okay, if you read this abuse notation carefully, that you have this is so what is this? X by y less than equals to A is W belongs to omega such that x of W divided by y of W is less than equals to A. If you read it carefully. And this is same as the set as W belongs to omega such that x of W is less than equals to A times y of W. Okay, both will share the same set since none of them is 0. Okay, so it is perfect to write. It is perfect to write this as x less than equals to A. It's no problem. Now we have dealt already with x strictly less than y. In a similar manner, we can discuss this limit now. X less than equals to AY. Okay, so you can draw the line passing through the origin, right? This is a line x equals to AY passing through the origin with slope A. You have this is A is strictly greater than 0, positive, right? So, and you can discuss the limit again. So that is going to be 0 to AY, x limits, and y limit is 0 to infinity. And since this joint PDF can be written as the product of marginal PDF. Okay, why? Because x and y are independent random variables. Okay, so this is why you can write this. Now you have the both the definition now. Fx of x is e to the power minus x, fy of y is e to the power minus y. And you are integrating with respect to x and with respect to y. Okay, now so if you go with the integration, you will get the following answer when you put the upper limit minus lower limit, everything. Okay, so for A greater than 0, you can differentiate this and you can find the derivative of this, right? You know, 1 by x derivative is minus 1 by x square. You are differentiating with respect to A here because you have evaluated with respect to A. Okay, at point A. So at point A, derivative is 1 upon 1 plus A whole square. Okay, and you have, which will give you the PDF of x by y. Okay, for A greater than 0, otherwise 0. So you can, okay, you can work with this. If you have any doubt, you can ask. Okay, right. So now we are going to moving forward to define a definition, so-called expectation of random variable. Okay, so everyone will be interested if you repeat a random experiment, okay, up to certain amount of time, and you are specific about the random variable as well. It's like suppose you have tossing a coin, you have tossed a coin 5 times, and you have noted down all the outcomes. Okay, it may be T, H, H, T, T. Okay, all the possible outcomes, and you are repeating, let's say 10 times that experiment. So X will denote the number of heads in each experiment, and so on. Means like you can associate the probabilities and so on. Now you are expecting in the means like suppose in the long run, how many number of how many number of head it will appear. Okay, so how will you answer that question is you have to certainly talk about weighted probability. Okay, so you have to certainly talk about the weighted probability. So in the first case, you may be not getting none of the head, or one head, or two head, three head, four head, five heads, not all of them are head, and they are equally likely. You can identify means all the things means. Okay, so you are going to work with a weighted probabilities. Means you are weighted means there is weight is attached with the probabilities. So what is the weight here is the X values. Okay, so X denotes the number of heads, means it can be 0, 1, 2, 3, 4, 5 into probability of getting 0 head, probability of getting 1 head, probability of getting 2 head, and so on. Okay, so these will turn out as a weighted probability. Okay, right. So this is what you can say in the long run. How many number of heads it will be depends whether your coin is biased or it is unbiased coin. Means getting a probability of head is 1/2 and probability of getting tail is 1/2 in a single toss. Okay, and or it is 1/4 or 3/4. It's a biased one. Okay, so it certainly depends. Okay, that what is the expected value means how many number of head in the long run you will be getting is 3 or 4 or 2, depends on the case. Okay, right? So that's okay, that's a motivation you can see. Okay, right. So let's define this. So let X be a discrete random variable that assumes the following values: x1, x2, x3, and dot 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 is here, means it may be countably finite, infinite, discrete case. Okay, then the expected value of X is nothing but the weighted average of the values of X. You multiply each probability with its corresponding value X, and then summing up all the values. Okay, overall. Okay, so that will give you the definition of expectation of random variable. Now let's try to understand by some examples. Okay, so let's take the first example. Let's take X value, assume 0, 1. Okay, with probabilities 1/2 each. Okay, so what you can expect in the long run or expectation of X is, if you go with the definition, it's nothing but the 0 into 1/2 is see 0, it will occur with probability 1/2. So 0 into px of 0 plus 1 into px of 1. Okay, so 0 into 1/2 plus 1 into 1/2. So that's going to be 1/2, which is nothing but the average of this. Similarly, this will follow whenever you have taken two numbers equally likely. Okay, so both are occurring with the probability 1/2. So then their expectation of X also can verify that this is nothing but the mean of these two. Okay, or average of these two numbers. On the other hand, so now if you take, instead of that unbiased one, you take the biased one case. What it gives you, it turns out to be something number 0.75. So that's very this definition is 0 into 1/4 with probability 1/4 plus 1 value it will take with probability 3/4. It's 3/4, and which will solve it on 0.75. So what it tells you, in the long run, it is going to close to what? 1. Okay, it is going to close to 1, right? 0.75 is close to 1. So it's long run, it's a high probability that you are going to get the value of X is 1. Okay, this is how you will interpret this. Okay, and see, you cannot expect expectation of x as sum of the number from the range of x. Okay, it may be or it may not be. You may be getting many times the decimal number. Okay, and so on. Okay, right. Now let's have another example. Okay, so let a random variable x denotes the outcome when we roll a fair dice. So rolling a fair dice means x will take the values 1, 2, 3, 4, 5, 6. X denotes the outcome when we roll a fair dice. That outcome is either 1 to 6. And let's assume that all of the number are or all of the outcomes are equally likely. So what is the expectation of x? Okay, so if I just try to interpret what it is you have, it will take x value is 1 into probability px of 1 plus it will take 2 value into probability of occurrence of 2 plus 3 into px of 3 and so on plus 6 into px of 6. Now these all are equally likely. You can take all of them are out and nothing but the 21 by 6 you can verify, right? 1 to 6 you can write 6 into 6 plus 1 by 2 something, right? So this is nothing but the average of this. Equally like if you take the equally likely case, it's nothing but the mean. It's nothing but the mean of that, right? Okay, right? And what it tells you 7 by 2 expected value of x is 7 by 2 and what it is close is 3.5, right? 3.5 is close with 3 and 4. So in the long run it is expected that you will be either getting 3 or 4 on the outcome as of a rolling a pair dice. That's the expected value, but not sure again. Say expected. Okay. Now, once you talk about this x, you can certainly talk about now. I am now going to define what do you understand by this x square. Okay. Okay. So we are going to identify this. Okay. Right. So this again function, right? You know, x square is what? X into x. You know how to define the product of two functions, f and g. Okay. So this is the same way you will define the x square here. Okay. So you have this is I'm just going to here. So if you are given with x, okay, if you are given with x is given, okay, means x is given to you. Okay. Now what is x square? For example, is going to be what is the range of x square of omega is nothing but the x square such that x belongs to omega. Straightforward. Okay. Or in other words, instead of this, I may take this is as n, x to the power n. Okay, x to the power n. N is any you have this n is natural number. This is a justified. Okay, there's no question about it. So for the above case, when you have x belongs to 1, 2, 3, 4, 5, 6, then x square belongs to each one will be squared 1 square, 2 square, 3 square, 4 square, 5 square, 6 square. And that is nothing but 1, 4, 9, 16, 25, 36. Similarly, you can identify the x cube. Okay, similarly, x cube. X cube belongs to 1, 8, 27, 64, 125, and this is 216, and so on. Okay, so why I'm going through this is because I want to identify if a given x and its associated probabilities Okay, probabilities values. I am able to identify the expectation of x. Okay. Now, can I relate this with the expectation of x to the power n? Okay, expectation of x to the power n or not? Okay, so this is what your goal is to define. Okay, right. So now let's. This is one example that you can follow from that recorded video at YouTube. Fine. So just a minute. This is okay. Okay. Now let's try to understand now. In this case, in this case itself. Okay. Let's have. Let me try to answer here the following. Okay, so let's consider the case x square. Okay, x square for that exercise, x square belongs to 1, 4, 9, 16, 25, 36. Okay, x belongs to 1, 2, 3, 4, 5, 6, and you have this is px of I is equals to 1 by 6, or I is equals to 1 to 6. Okay, this is all given to you. Now, I am interested in expectation of x square. So if you define this, if I say let y is equals to x square and follow the definition, then expectation of y is equals to, because y is also discrete, is going to be y times probability mass function of y. Y belongs to y of omega. This is what the definition, right? This will be the definition. So you have to identify the PMF of this x square. Okay. Now, if you define the PMF of x square, let's see. Okay. So now Py of 1, what it is by definition? Probability of y equals to 1. That's equals to probability of y is what? X square equals to 1. Now, this is equals to x square equals to 1. So there are two possibilities. X is minus 1 and 1. But you can look at back and see x can only take one value, not the minus 1. So it is equals to probability of x equals to 1. Other case is impossible event. That will not contribute anything. So this is equals to px of 1, and that's something like it is given to you 1 by 6. Now, similarly, you have py of not 2, it is 4. Py of 4 is equals to probability of y equals to 4, and that is equals to probability of x square equals to 4. So that's equals to probability of x equals to 2, and just I'm going to write it here as it is. So px of 2, that's going to be 6. So x square equals to 4. We'll again take two possibilities, minus 2 and plus 2, but x minus 2 is not possible. It's an impossible event. Okay, so it's going to be again take the values. So similarly, py of you have 9 can be shown as px of 3. Py of 16 you can show that that's going to be px of 4. Okay, py of 25 can be shown to be px of 5, and you have py of 36 can be shown as px of 6. So if I go back and see here, so now I can now say from here above discussion that this will implies expectation of y is equals to summation y belongs to y of omega. Okay, and that's going to be, you have y time. So px of x, what is x is root y, right? Square root of y, positive. Okay, right, for this case. Right, Okay, or now if I want to write in the case of so this implies expectation. If I write everything in the x square form now, summation y is x square and root y is x, and you are summing over the values of x. So the x belongs to x. Now your exercise is to show, okay, your exercise is now show that expectation of x cube in this particular case is summation x belongs to x of omega times x cube times px of x.
Hello, sir.
Yes.
Sir, in the first formula, how expression of y came to be summation over y of y times px of under root of y.
See how if you relate it, you see y is, see this is 16, 4 is a square root of this, right? So this is y value and you are taking the square root of this, positive square root. I'm not attached here plus minus here. So because only possibility is plus.
Yes, sir.
Okay.
Yes, sir.
So
Yes, sir.
9, 3, 4, 2, 1, 1. Right? 36, 6, so 25, 5.
Yes, sir. Understood, sir. Understood, sir. Understood, sir.
So here, if you go with the similar notation, you will have cube root of y and so on. If you go for the nth one, so you have nth root of this y, 1 by n. Okay? In general, this is going to be for this x square, so you can generalize this to, so you can show that you can say mathematical induction, or you can, instead of mathematical induction, you can hire by using the principle of mathematical induction also, you can show that this is going to be summation x belongs to x of omega x to the power n times px of x. Okay, right. Now this is case for discrete case. Okay, so now in the case of continuous, so discrete case we have defined the expectation as the summation, right? In the continuous case, if you continuous random variable, you will have an integral over the x values. Okay, so weighted probabilities on where the weighted probabilities are, so probabilities one you have identified. So if you are just going to the definition now, there you will see. Okay, so let x be a continuous random variable, then the expectation of x will be defined as you multiply fx of x by x. Okay, and then you are taking the integral. Note that you have already we have already said something here that dx, for small dx we have this fx of x dx is can be look at as like a probability over between the interval x to x plus dx. This is one thing. Okay, right? So for the weighted probability, you have to multiply both sides by x and then integrate. Okay, right. Now let's do one example here, which is an example of a uniform random variable. So I'm going to define that also. Okay, so so you will be I will define it. Okay, let me define it. I will say so uniform random variable. So we say that a random variable x is uniform okay, over uniform over close interval AB if its PDF will be fx of x is equals to, over this interval you have uniform, right? Uniform length, right? 1 upon b minus a. 1 upon the length of the interval whenever x is lies between a to b. This is a b to b, close interval or open interval. Okay, doesn't matter, and 0 otherwise. And we denote, okay, we denote x follows uniform distribution or the interval a to b. This is what is a notation. Okay, your exercises find out the mean of this. Okay, expectation of or expected value that you can find out. We will come back. Okay, right. Now let's look at this example. Suppose that you are expecting a message, okay, at some time past 5 p.m. Okay, so from your experience, past experience, you know that x, the number of hours after 5 p.m. So that denotes, x denotes the number of hours after 5 p.m. until the message arrives is a random variable with the following periods. Okay, so if you know by your experience that the number of hours means it may delay, okay, or it will arrive to you, okay, until the message arrive is a random variable. Anytime it can arrive, and that follows the uniform distribution over the interval 0 to 1.5. Okay, now in that case, find the expected amount of time past 5 p.m. until the message arrives. So means you are interested in finding the expectation of x. Okay, you are interested in expectation of x. Okay, and that's very simple to follow now. So x times fx of x, if you follow the definition, and you know fx of x is only known 0 between 0 to 1.5. Okay, so and fx of x will take the value 1 upon 1.5 over this interval, and you can integrate it, and 0.75 expectation of x is 0.75. So the hour 0.75 hours expectation of x. So if how it will be, it will convert to the number of, I mean the time one, what it will be is about 45 minutes, right? 75%. Okay, approximately 45 minutes later you will arrive, the message will arrive to you. Okay, right. Now, so now just now we have discussed the expectation of x to the power n. Okay, x to the power n in case of discrete random variable. Okay, so that can be extended to the continuous case as well. Okay, or in general, okay, or in general, expectation of a function of random variable x can also be identified. So a function that is a more general one. So instead of x to the power 2 or x power 3, now you can work with sine of x, cos of x. Okay, means x follows continuous random variable, and sine of x will follow the sum of the distribution. Okay, sine curve or cosine curve, and so on. You can take now any function. Okay, how will you define the expectation of that function of random variable x? Okay, so we have already gone through one example. Okay, so this this is a let x be discrete. I think this is already discussed with respect to case x square and x cube in the video that you can refer. Okay, so I'm just going to again, we are going to work with the similar way, right? X belongs to 0, 1, 2. X is having the range is 0, 1, 2. Okay, and the PMF of x is given to you at 0, at 1, and at 2 values are given, and you are expecting x square and x cube. Okay, so certainly you have this x belongs to 0, 1, 2. Here this is all given. X square is 0, 1, 4. This is all discussed, okay, just now. So expectation of x square can be evaluated in the simulation. Similarly, x belongs to x cube will lies in the interval 0, 1, 8, and that is also find out that px cube of 0 is px of 0, px cube of 1 is px of 1, px cube of 8 is you have px of 2, and you can all relate in the similar way. Okay, so then you will have the expectation of x cube. You can follow the definition. Okay, so there's nothing to discuss here. Okay, I just now, yeah, this can be discussed. This problem can be discussed little. Okay, now this problem is the time in hours it takes to locate and repair an electrical breakdown in a certain factory is a random variable with following PDF. So again, x is a uniform distribution over the interval 0 to 1, that also can be followed. Okay, now what is given is if the cost involved in breakdown of duration x is x cube, means whatever the number of hours, we are charging the cube of that. Okay, 1 hour is 1 cube, it will be maybe at $1 or 1 pound or 1 rupees or whatever. Okay, so what is the expected cost of such breakdown? Okay, so what is the expected cost of such breakdown? So I'm interested in this. So certainly you need to, so I'm going to show you here that in the case of continuous also the situation will be the same. So in order to do so means you are trying to find the expected cost of such breakdown. Okay, so cost is related with the time by x cube. Okay, so you know the distribution function for the random variable x. So you need to identify the random variable corresponding to the random variable x cube. Okay, so if you x denotes the time, means the total time. Okay, which is following uniform distribution over 0. And you are interested in the cost. Cost is x cube. Okay, that is total cost. Okay, so how what will be the distribution? That can be identified by first finding the CDF distribution function we will look at. Okay, so you can identify the cumulative distribution function for x cube. Okay, and then you can differentiate and you can identify the density function, and then you can get back to it. Okay, right. So here it is. So x. So you have, this is x cube of a. We are starting with this. So x cube of a. This is a you have now x cube less than equals to a. If a is less than equals to 0, there are two possibilities. A is less than 0 or greater than 0, right? Because of the x values lies between 0 to 1. Only non-zero you have that. You can consider that case. So a less than equals to 0, x cube less than equals to, this is an impossible event that will cause to the 0 value. In the case of if a is greater than 0, you have x cube is less than equals to a, you can write in the following form. Right? Because none of them is negative number. Okay, we are talking about only the case when x is greater than 0. Okay, and you know PDF is only non-zero over the value x positive value, so we can go with this. X cube is less than equals to a is implies x is less than equals to third or cube root of a. And now you can certainly go with the definition now, minus infinity to a to the power 1 by 3 fx of x dx. Okay, now again, so if a is greater than 1, if a is greater than 1, this value is 1. Why? Because fx of x is a to power 1 by 3 is 1. Okay, so only need to discuss between a value between 0 to 1. Okay, so between 0 to 1, so 0 to a to the power 1 by 3, whenever a is less than 1, fx of x value is 1. Okay, and you have, if you integrate and all, you will get a to the power 1 by 3. Okay, so this is what you get. A is less than or equals to 0, the distribution of x cube is 0. Whenever a is lies between 0 to 1, the distribution value is a to the power 1 by 3. When a is greater than 1, the value is 1. Okay, and the PDF can be identified by just taking the derivative over the interval 0 to 1. Okay, so that's going to be 1, as you know how to differentiate, right? 1 by 3 times a to the power minus 2 by 3. And otherwise it will be 0. You can verify that this is going to be a PDF. It is a non-negative and it satisfies the normality condition. Okay, now you have this the density that density function for the random variable x cube. So certainly you can define now expectation. So expectation of y is equals to, you know, y times fy of y dy. So fy of y you just have found. Okay, you substitute here, you can verify. Okay, all this detail you can verify. Okay, 0 to 1 this limits, and you have the final value is 1 by 4. Now I wish I'm giving you an exercise here that you can verify that expectation of x cube instead of expectation of x cube, this value x cube times fx of x dx. If you do multiply the PDF of x with x cube and integrate over the whole region, it will give you the expectation value of the given example. That's going to be 1 by 4. Okay, that you can verify. So for this example, expectation of x cube is equals to this value as well. Okay, so this is not limited to this. This is going to be, can be generalized to anyone. So similarly, you can go with x square also. You can verify. You can verify with x to the power 4. Okay, and so on, x power n. Okay, right. I think we can close here. Okay. If you have any question, you can ask.
Sir,
Yeah.
sir, can you share the lecture slide?
Okay, I will share. I will share with the parallel to the YouTube lecture. Okay.
Sir, actually the previous lecture slide, I guess.
Okay, I will do that. I think I missed. I will do that together.
Thank you, sir.